Hello. What I'd like to talk about today is the fundamental theorem of linear algebra. And I will explain what is that, and then I'm trying to give a proof for that. Basically, what the theorem said is if we consider the row space and column row space and null space of some matrix. So for some matrix A, so I will define what is row space and null space, but let me define it first, maybe. Like basically, if you think of any matrix A here, and if you think of the rows of this matrix A, I can just partition this matrix into rows. Let's hit this A matrix is n by n, so that's like m rows here, and each rows have a dimension n. So that's A1 up to AM here. And so if I think of like all the linear combination of the rows there, that will span a space, right? So more precisely, the row space of A will be basically just equal to the linear combination, basically all the possible combination of AI multiply, okay, maybe, yeah, that's okay. I use AI here. Please understand this is a vector, and multiply by scalar, let's say Ci here, okay. And this is I, so this one is scalar, this is a vector. And for all combination of Ci, so Ci is just real number, basically. Real. And this I is something from 1 to m. So very simple definition. So for example, if I have a matrix, let me just give a concrete example. Like 1, 0, 0, 1, let's say, right? Then the whole space is basically just the entire 2D space. To, so I have like this A1 is like 1, 0, A2 is 0, 1, and basically any points on the 2D space can be spanned by these two vectors, right? So so therefore the whole space is just the entire 2D space. And then the null space of a matrix will be just if I have a vector. So again, let's say this matrix is n by n. So if I have a multiplied by some vector x, let's say, x therefore should be n by 1. And if this is equal to 0, then we say that x is in the null space of A. So therefore, the null space of A is basically just for all vectors satisfy Ax equal to 0. And now the fundamental theorem of linear algebra says that um, the row space and null space are perpendicular to one another, meaning that if I pick any kind of vector, let's say I have x in this row space of A, and then I pick a y in the null space of A. So x and y will be perpendicular, or the inner product will be equal to 0. So the inner product will be if the domain here we consider all the real matrix, so it will be just simply x transpose y is equal to 0. So by the way, the convention we are using is always say all the vectors are column vectors here. So and perpendicular, this is the geometrical meaning is also is perpendicular because when I have the inner product of this is actually just equal to the ln of x multiplied by the ln of y multiplied by cosine theta, right? So if this is equal to 0, the angle between this x and y, this theta here, has the cosine theta of this theta of this angle here should be 0. So therefore the angle should be 90 degrees. So therefore like the two vectors are perpendicular. Now I'm also like say something more. So I guess I would say this is two things. Right? This is one thing. This other thing is like the row space and the null space essentially span the entire space. Or usually people will write it something like the dimension. If you think of the dimension of the row space plus the dimension of the null space will be just equal to n. So I have each of these vectors in this Rowspace and nullspace are n-dimensional vectors, right? And these two spaces are perpendicular to one another, but when they add together, they span the entire space. So geometrically thinking, say again, if you have I'm in 2D space here, or let's consider 3D space. So I can have the whole space. Let's say this is like xy, this xy z. Let's say so, and I can have the xy plane here. This is the xy plane. Maybe it's the whole space. Let's say this is the whole space. Oh, I don't know why I'm sorry. Like I write wall here, but yeah, it doesn't matter. Anyway, yeah, it's okay. Okay, let me change it anyway. So whole space. Yeah, this is the whole space, and let's say I have let's use a different color again. The C axis here, along the C axis here, this is the null space, I say. So the whole space and null space essentially span the entire space. Because if you think of any vector, can be a linear combination of this whole space plus this null space. For example, if I think of like any vectors, maybe somewhere here, and this vector is equal to this vector here that's in the whole space, at this vector here is in the null space. Okay. So we're going to prove that. It turns out the proof is quite easy, especially the first part. Actually, the first part is very easy. The second part, I will just have my own proof. I guess I won't say it's original. I'm quite sure like someone did that before, but I think it's a pretty elegant proof. Like so. So let's look at the first part here. The first part, like whole space and null space are perpendicular to one another. Now, what we need to do is just like, let's say I have any x here. Let's say x is in the null space. So therefore, like ax is equal to 0. Now, ax equal to 0 saying what? It's saying that like I know that like ax itself is actually is a vector, right? So this is actually an all 0 vector here. So and my a here is actually is a1 up to am, right? Times x here equal to 0. So it means that like what I have here is really sorry, I should probably get closer to the mic. What I have here is really a1 times x. I have ai times x. AI transport. Wait, that's fine actually. Or maybe I use inner product to write it like ai times x is equal to 0, right? So therefore, like for each of these ai's is like perpendicular to x. Then of course, like for any vector in the whole space of A is linear combination of all these A's, right? So therefore, like any vector in, let's say any vector y in the whole space, I will have like y is equal to ai, maybe I put it that way to emphasize that, ci, something like that, right? And if I try to do the inner product with x here, so that will give me like I, ci, ai, x. So this will be 0 because like from here, this will be 0. So therefore like this will be 0. So any any vector in the whole space will be perpendicular to any vector in null space. So therefore, like, okay, I have this shown. So the first one is actually pretty easy. So for the second one, so what we want to show is like, let's think of like if we have for the second part here. So I will prove the first part for the second part here. The second part here. Think of any vector y here. So like the vector here, at this y here, maybe I use this blue color here, the y here. As I said, like we can split it into, let's say, if both space and null space span the entire space, then y should be able to split into y1 and y2, and y1 in the whole space and y2 in the null space. For example, like I can have like this part is y1 and this part is equal to y2. Okay? And so the trick here, okay, or like the idea is like I should think of like if I can figure out what is y1, then I can find y2. I just want to make sure that y2 is indeed in the null space, and that's how we are going to do that. But before that, like we need to make several. I want to give several assumptions here, and that those assumptions they didn't. It's just make the problem a little bit simpler, and it doesn't actually without loss of generality. So first thing, like we can assume that A is I mean all rules A1 up to AM are linearly independent. So we assume basically the matrix is full rank, in other words. So otherwise, let's say if I have like some of the rows are not linearly independent, it doesn't matter. Let's say if I have A here is A1, A2, and maybe just A1, A2, A3, and so on. And let's say A3 is a linear combination of A1 and A2. Now, if I remove A3 and I get a matrix A tilde instead, it's just A1 and A2. The row space of A will be apparently just the same as row space of A tilde, right? Because row space of A, meaning that like if some vector A is in row space of A here, if this is inside X is inside row space of A here, it'd be linear combination of like A1, A2, and A3, right? So again, maybe by C1, C2, and C3 here with the coefficient. So now, because A3 is just linear combination of A1 and A2, right? So I can just replace this by like maybe some A1 times D1 plus D2 times A2. And then I can regroup the term. And then apparently this X is just linear combinations of A1 and A2 only. So therefore, like the row space of A will be just the same as the row space of A tilde. So, and of course, or like actually what I say is like any element in X row space of A, what I just show actually would be okay, to be step by step, what I just say is actually really row space of A will be inside the row space of A tilde, but apparently row space of A tilde will be in row space of A, because I trying to do linear combination of like one less vectors. Of course, like the space will be smaller. So therefore, like these two spaces are the same. Now, also, like I know that like not just the row space is the same, but the null space will be the same as well. So if I consider like a vector X, let's say, in the null space of A, so I have like AX equal to 0, right? But AX equal to 0 will first of all, like x is equal to 0 imply a tilde x equal to 0, right? So I will have apparently like null space of A is inside null space of A tilde. Now, but note that the other part like is not exactly trivial because this is apparently true because I essentially remove one equations, right? Because when I say ax equal to 0, I mean like a1x equal to 0, a2x equal to 0, and a3x equal to 0, right? And a2 to x equal to 0, it means a1x equal to 0 and a2x equal to 0. This is all in the product. Then, of course, if I have this, I ignore one more equation. I still have this 2, so therefore, like null space of A will be inside null space of A tilde. But, okay, but I can also show that null space of A tilde is also inside null space of A. So let's say if I have A tilde x is equal to 0. Now A tilde x equal to 0. Of course, I have A1x equal to 0, A2x equal to 0. But also I will have A3x will be equal to 0 because A3 is just linear combination of A1 and A2, right? So I will have A3x is equal to some, let's say D1A1 plus D2A2x. Then again, I have D1A1x plus D2A2x. So therefore this equal to 0. So therefore it's equal to 0. So again, I will have like, I will have basically both. So therefore like, again, like the null space of A is equal to null space of A tilde. So therefore you see like it doesn't matter like if I remove the any rows there's linear combinations of the other rows. So therefore I can assume that all the rows are linearly independent. Okay, that's my first assumption. Maybe I should put it down here. Okay, yeah, actually I put it down here already. All rows even are linearly independent. So, and another assumption is not exactly an assumption, but I will only consider the case that like A is fat. So, of course, since we already assume that all the rows are linearly independent, I cannot have like n bigger than n. So I cannot have a tall matrix. Otherwise, I will have some of the rows are linearly independent. So at most, I can have m equal to n. In general, m will be less than equal to n here. But we'll assume m is not equal to n. M is not equal. M basically we'll assume that m is strictly less than n. So because for the case when m equal to n, again, it's like something is trivial. In that case, it's not again, it's trivial, but it'll be a trivial case when m equal to n. So let me just write it down here. So actually from here, we already implied that m is less than equal to n, but we can consider the case when m equal to n, but m equal to n, the case will be like the row space apparently will just span the entire space, right? So because I have like n linearly independent vectors, they will span the entire space basically. This is a just think of if you're a 2D space, you have any two vectors, they are not linearly independent to one another. Then if you give any points here, then this can be considered as linear combination of this vector along, okay. Yeah, add with like this vector here, right? So therefore, like any point in the 2D space can expand by the so basically like this will cover the entire space. I want to say the whole space will cover the entire space, therefore it's just equal to Rn here. And the null space in that case actually it would be just equal to 0, only continue 0 the element, because I have ax equal to 0 and x is full rank. The only solution here would be x is equal to 0. So therefore, like in this case, yeah, actually, even I have this already, like is sufficient to show that this span the entire space. So, but actually, I already done when I have this here. So, so therefore, like in general, okay, let us consider more interesting general cases like m less than n. So now let me erase this now here. So my assumption here is that like all the rows are linearly independent, and m is less than n. And my approach, as I said, is I will just, for any vector in the n-dimensional space, let's say y in Rn, I will just split it into y1 plus y2. So I hope y is equal to y1 plus y2. And I will try to find y1 in the row space. It superpose row space of A, and y2 in the null space of A. So the idea is like, okay, I probably should find the y1 is exactly the projection of y on the row space. So that probably give me the best solution there. If that's, I find the projection of y to the row space y1 here, y2 should be perpendicular to y1. And if in that case, then y2, we kind of expect that y2 should be linearly independent. Oh, by the way, like I'm not sure, I didn't even mention that why, maybe some of you may ask like, why I need to show this. Isn't that like only the first part is sufficient? Know that like if I only show that row space and null space are perpendicular to one another, I may have the row space that's not row space and null space does not cover the entire space. For example, like I may have the in a three-dimensional space, I may have the null space is the c-axis, and then the row space may be just the x-axis. Then I also have this row space perpendicular to this null space here, but it doesn't cover the entire space. So okay, anyway, I think it's something trivial, but like I just want to clarify that. So anyway, now back to the proof here for the second part here. Now let's say I have y here. What I'm going to do is I say like y1 should be on the row space of A, right? So therefore y1 should be equal to some linear combination of the rows. So in other words, okay, if I put y1 as a column vector here, so y1 should be equal to A transpose multiplied by some z here. So, and if I want to find the optimum projection here, yeah, if I say it's just the projection, I guess it's not just maybe the optimal solution here. I would like to have something like y is cup equal to A transpose C here. So that will be just solve a least square problem. So the way to do that is I can multiply A on both hand sides. So I have AY is equal to A transpose Z, let's say. So I shouldn't Y in Y. Yeah, it's okay. Let me just Y equal sign anyway. So and then my C here, so therefore they will be equal to A transpose inverse AY. So basically I multiply A transpose inverse on both sides. So then this I got cancel on this side. I have yeah, this is equal to C. Yeah, C is equal to this. So if I pick C equal to this probably will give me the best projection. So therefore, my guess is I will have like y1 is equal to A transpose, A transpose inverse AY. And know that I don't care about like this whole thing look complicated, but know that this is in the Rowspace of A because it's like A transpose multiplied by some vector, right? This thing is complicated, but after all, it's just some vector, right? So therefore, this Y1 is indeed in Rowspace of A. And now, if I consider the difference of Y minus Y1, I would say like Y2 define Y2 is Y minus Y1. So therefore, it's equal to Y minus A transpose A transpose inverse AY. I will claim that like Y2 is in the null space. Actually, I don't even need to claim that. Like we can see that immediately because we can show this immediately because AY2 is equal to A Y minus A transpose A transpose inverse AY, right? So then I have AY here minus A transpose A transpose inverse. So this A transpose and A transpose inverse got cancelled. So I have AY left. And this is super nice. It's AY minus AY is equal to 0. So therefore, like indeed, like Y A multiplied Y2 is equal to 0. Therefore, Y2 is in the null space of A. So therefore, I have Y equal to Y1 plus Y2, and Y1 is in Rowspace of A, and Y2 in null space of A, and Y is any Y. So therefore, like it span the basically the Rowspace and null space together span the entire Rn space, and this complete the proof. Okay, that's all. Okay, thank you for your listening.